Good morning. One of our subscribers asked the following question. How do you sketch the graph of a cosine function by just looking at or analyzing its equation? This is a very good question, and in order to answer this, we need to follow the following steps and sequence until we arrive at the point when we are ready to answer that question. So the sequence of this presentation is we are going to talk about the transformation of the graph of the cosine function from the parent function up to our specific cosine function. So the first step is we ask ourselves, what is a cosine function? Then we will graph the parent cosine function. Then we will do the translation of the cosine function first vertically and then horizontally. And then we look at how to reflect and dilate vertically the cosine function. And then finally, we'll do the reflection and the dilation of the cosine function horizontally. Once we go through these 6 mini lessons, then we'll come to the point when we are ready to identify and describe the graph of the cosine function by just looking at or analyzing its equation. So let's begin with the first mini lesson. What is a cosine function? So by definition, if we have a right triangle, we define the cosine of the angle theta to be the ratio of the adjacent side. So this is our adjacent side. With respect to this angle theta, the length of this side and the length of this hypotenuse, when we get the ratio of the length of the adjacent side to the length of the hypotenuse, we are getting the value of the cosine of that angle. I would like to credit mathopenref.com for these visuals. For example, we have this triangle. And we can move this point so we can adjust the measure of the angle. If the angle, let's say, is at 30 degrees, you will notice that the ratio between this adjacent side, which is 9.1 unit, divided by this hypotenuse, which is 10.5, is equal to 0.87. And that 0.87 now is the cosine of 30 degrees. In other words, this cosine just says get the ratio between the adjacent side and the hypotenuse of a right triangle. Now, I would like you to look at this animation. If I change the measure of this angle counterclockwise, you will notice here in this part that the ratio of the adjacent side to the hypotenuse changes, and look at the change. As we trace the value of the cosine, as we change the value of the angle, I want you to look at this red curve. If I keep on changing the measure of the angle, we are forming what we call as the cosine wave. If, on the other hand, let me reset this. If, on the other hand, I move to the other side, clockwise direction, notice that after 0 degree angle, you look at this angle here, after 0 degree, we go to negative angle. and the corresponding movement of our cosine wave is going to the negative direction in the x-axis. And we just keep moving and rotating and rotating. And if you think of this point as a particle, it travels like a wave. That's the idea behind the cosine wave function. So let's go back this part. So we have the cosine as the ratio of the adjacent over the hypotenuse. There's a special length for the hypotenuse that we generally use when we are determining the sine or the cosine value of the angle, because you can observe that if we have a triangle that looks like this, and this is the angle, if we call this as A and C, the ratio of A over C equal to cosine of the angle. If we are going to extend this and extend this side also to form another similar triangle, so a blue triangle similar to the red triangle, the angle is the same for both of these triangles. And if we call this as our A prime and we call this as our C prime, the ratio of A prime over C prime would still be equal to the ratio of A over C. So there could be a lot of triangles with the same reference angle here. In our case, let's say it's 30 degrees, but you can form a lot of similar triangles with that reference angle, and the cosine of that angle would always be the same because the ratio of the adjacent side A to its corresponding radius C would still be the same as the ratio of A prime to C prime. So to simplify our computation for the cosine function, we will look at the special case when the length of the hypotenuse is 1 unit. And if we put a unit circle around, if we put that like this one, you have a circle, and we inscribe that triangle. If that circle is a unit circle, then this length would always be 1 unit. So the radius would also always be 1 unit, which is the length of the hypotenuse of the triangle. That's what we are going to do in the next slide. So let's look at special right triangles. So the first special right triangle that we're going to look at, a 45, 90 right triangle. So 45 here, and a right triangle. If this is 1 unit, what are the lengths of these two legs? Since this is a 45, 90 triangle, this length must be of the same measure as that other leg. And using the Pythagorean Theorem, we can now say a squared plus b squared equals c squared, where our a is x and our b is also x and our c is 1. Then we have 2x squared equals 1 squared is 1. So x squared equals 1/2. x is the square root of 1/2. And then we can rationalize the denominator, multiply by square root of 2/2. So we have x equals square root of 2/2. So this length is square root of 2/2. And this one is also square root of 2/2. For the cosine of 45 degrees, that is equal to the ratio of the adjacent side with a length of square root of 2/2 and a radius of 1, will get square root of 2/2. So we therefore say that the cosine of 45 degrees is square root of 2/2. Look at now our table here. The cosine of 45 degrees is square root of 2/2. This number is very important when you are dealing with trigonometric functions. So remember that the cosine of 45 degrees is square root of 2/2. The second special right triangle is the 30, 60, 90 right triangle. So this is how we are going to do this one. Let us create an equilateral triangle, and let us drop a perpendicular bisector. The length of this be 1 unit, and the other side is also 1 unit because it's an equilateral triangle. But since we dropped a perpendicular bisector, we have 1/2 and 1/2 here. Then let's focus ourselves on this right triangle. So we now have, if the triangle is an equilateral triangle, it follows that it's equiangular. So the length of the angle here is 60 degrees. It's also 60 here, but since we bisected the angle, this angle therefore should be 30 degrees. And this is perpendicular, so 90 degrees. So we have a 30, 60, 90 right triangle. And we said this is 1 unit and this is 1/2. So from here, we therefore say that the cosine of 60 degrees is equal to the adjacent side, which is 1/2, over the hypotenuse, which is equal to, which is 1. So 1/2 divided by 1 equals 1/2. So cosine of 60 degrees is 1/2. That is also what you have here. Cosine of 60 degrees is equal to 1/2. So how do we find the cosine of 30 degrees? So what we're going to do is just look at the triangle from a different perspective. If our reference angle is now this 30 degrees, then with respect to this angle, its adjacent side would be this one. And this is still the same hypotenuse. So what is the length of that side? We can compute again using the Pythagorean Theorem. So from a squared plus b squared equals c squared. Okay, you have 1/2 squared plus the length of this side, let's call this b. So plus b squared equals 1 squared, which is 1. So therefore we have b squared equals 1 minus the square of 1/2, which is 1/4. And then b squared equals, therefore b equals the square root of 3/4, which is equal to square root of 3 over square root of 4, 2. So the length of b here is square root of 3 over 2. So therefore for the cosine of 30 degrees, we now have its adjacent side with respect to this angle. The adjacent side is square root of 3 over 2 divided by the hypotenuse of 1. So still we get square root of 3 over 2. That is the reason why the cosine of 30 degrees is square root of 3 over 2. By knowing these values of the special right triangles, we'll be able to graph the parent function of the cosine function. Okay, now let's look at the graph of the parent function of the cosine function. So the graph of y equals cosine of an angle theta looks like a wave like this. If you let the angle be equal to 0, the cosine of 0 is equal to 1. If we move the angle to 30 degrees, the length of this side is square root of 3 over 2 from what we derived from the previous lesson. And if you are going to compute the decimal value of square root of 3 over 2, square root of 3 divided by 2 equals around 0.87. That's why if you are at 30 degrees, this length is about 0.87. And then if you are at 60 degrees, we know that the length of this side is 1/2. That's why at this point you have 1/2. And then at 90 degrees, the x value is at 0. So we have 0. And then when we go to the other side, we just change the sign for the cosine. And then it's a repeating wave. Now what happens if from the parent function y equals cosine theta, we transform the equation into y equals cosine of theta minus 2? I would like to show you an animation for that. So basically this is the transform formula for the cosine function. This c will have an effect of moving up or down the graph of the parent function. So let's move that c. Notice that if I move the c up to the right, the graph moves up. If I move the c to the left, that means I decrease the value. The parent function graph goes downward. Therefore, we now say that c translates the parent function up or down. So it's the vertical translation. Now, let's look at what happens to the graph if I change this a. The a affects what we call as the amplitude. If I move this c up or down, look at what happens. So going to the right means I am increasing the height of the cosine function. And then let's go back to 0, to 1. What happens if I get a value between 0 and 1? So let's say 0.94, 0.9. We are shrinking the graph vertically. But there's a limit to where we can shrink it, because at 0, the graph would be a straight line. And then if we move to the negative side, we are reflecting the graph across the x-axis. It's taller and taller, but it's now the reflected version of the cosine function, because originally it looks like this. If we move to the negative 1, notice that it used to be a wave going this way, and then we reflect to the other side at negative 1. So you can see the reflection. It's like a mirror image where the x-axis is the mirror. So therefore, the effect of A is to change the height of the function, and if we change the sign of A to negative, it has the effect of reflecting the graph across the x-axis. Next, let's look at the effect to the graph of this D. So if I change the D, what happens to the graph? Let's reset to the parent function. If I change the D value, notice that this is minus sign here. If I move to the right, we are sliding the graph to the right. If I move to the left, we are sliding the graph to the left. So therefore, we now say that D affects the horizontal translation, sliding to the right or sliding to the left of the parent cosine function. And then finally, the effect of this K. Make sure that it should be in the form K times the quantity X minus D. So it should be in the factored form whenever the coefficient of X is not 1. So let's look at the effect of K. If I make K greater, the graph is like a spring that's squeezed to the center. So the higher the K value, the more squeezed is the graph of the cosine function. If we do the opposite action, if we decrease the value of K, notice that the graph is stretched. But when K equals 0, we can no longer stretch the cosine function. And when we move to the negative direction for the value of K, it has the effect of also reflecting the graph. But since cosine is an even function, the right side and the left side are symmetric with respect to the y-axis. You can see that the reflected image is just almost similar to the original parent function. So to summarize, the C translates the graph vertically up and down. The D translates the graph to the left or to the right. That is the horizontal translation. The K stretches or squeezes the graph. And the A increased or decreased the amplitude or the height of the graph And when we move to the negative direction, the a reflects the cosine function. So let's have some exercises to check our understanding. So if we have y equals cosine theta, if we subtract 2, these 2 will translate the graph down 2 units. So from this parent function, we now have this graph, means we just move this graph down 2 units. Whereas if we add plus 1, the parent function is moved up 1 unit. Next, from the parent function y equals cosine theta, if we add 90 degrees to the angle, this 90 degrees will translate the graph to the left 90 units, because this must be written in the form cosine of theta minus negative 90. So this negative 90 will move this 90 degrees to the left. That's why you now have this point corresponding to this point. So we are translating the graph 90 degrees to the left. Whereas if we have cosine of theta minus 45, we are going to move the graph 45 degrees to the right. So from this parent function, we move the graph 45 degrees. So that is now from here, we move the graph 45 degrees, and then everything is the same form. Next, if we have this parent function and we have cosine of 2 theta, these 2 now will have an effect of squeezing the graph horizontally. It should be noted that from this point to that point, we call that as the period of the cosine function. It's from here to that, we complete one cycle, and then all the rest are just repetition of the same cycle. And the length of this, that means the period, is equivalent to 360 degrees divided by whatever is the value here, the constant next to the angle. Our constant is 2, so divided by 2, 360 divided by 2, because of this 2, we get 180 degrees. That becomes the period of the function. So if you look at the parent cosine function, the period is from 0 degrees to 360 degrees, because it's implied that the number here is 1. If we included this 2 here, that means we are squeezing the graph by a factor of 1/2. So we divide 360 by 2, we get 180 degrees. So you'll notice now that one period is 180 degrees compared to 360 degrees here. So we squeeze the graph horizontally. On the other hand, if you have cosine of theta over 3, it implies that there's a 1 here. So the period would therefore be 360 divided by 1/3, or 360 times the reciprocal of 1/3, which is 3 over 1. So that becomes 1080. So the period is therefore 1080. Next, from the parent function cosine theta, if the number is before the function, this affects the amplitude or the height of the function. So here the height is 1 unit. If you multiply by 2, the height would be increased to 2 units. If this number is 1/2, the height becomes the 1/2 that of the parent function. And then what if we combine everything now? So this is the parent function. We now have this transformed function. So first, we need to do some factoring here. We need to write this as y equals 3 cosine 2 times theta minus 15 minus 2. You can check 2 times theta is theta, 2 times 15 is 30. So these two will change the period of the graph. So it will have an effect of 360 divided by 2 equals, the 2 is this one, equals 180. So the period from this point to that point should be 180 degrees. Now this negative 15, this minus 15 will have an effect of moving the graph 15 degrees to the right horizontally. That's why from the original position here, we move the graph 15 degrees to the right. That's why it's no longer centered at this point. We move 15 degrees to the right. This 3 will increase this height from 1 to 3. So therefore, it will look like something like this. That's the rough sketch. And then, because of this negative 2, we are going to move it 2 units down. 1, 2. So the graph would therefore be down like that. That's the sketch, the rough sketch. So that is now why the graph looks like this way. So by just looking at this equation, therefore, with our knowledge of the transformation of the cosine function, we'll be able to come up with this graph without writing a set of ordered points and computing for the y value and then plotting those points. We can get a rough sketch of the cosine function by analyzing what is the vertical translation, what is the change in the amplitude, what is the horizontal translation, what factor we use to stretch or to squeeze the graph, is there a reflection or if there is no reflection. This is the beauty of mathematics. There is a pattern such that when you know the pattern, everything just becomes easier.